Okay, this lecture is called the non-ideal diode. This may take several lectures to get through what we want to cover here, but here comes our non-ideal diode. If we were to just make up a circuit like this in lab, and I don't know, this might be a 5 cosine whatever wave. And if we were to look and see, so here's our input, that's not a cosine wave, okay, you know what I mean. So if we were to look at this cosine wave, what you might notice is that there's a little flat line here, and then it'll come up and come down, and then it'll flatline through there, and then it'll come up and come down. And there's two things. There's a little flat line. There's this little gap that exists right here, and there's also this gap that exists here. And this is because the one-way valves are not perfect. Imagine an actual check valve in a water fluid pump pipe, and we come through and at some point maybe we just have a gravity feed when there's a pivot, and this thing comes down in front of the pipe like this. So we have a pipe, and we try to push water through this way, and it pushes this, it moves it up into this position. There's a certain minimum amount of pressure that you have to push. Now, it's not much, but you have to push a minimum amount of pressure to get this out of the way. It also slightly resists the flow in the pipe. And then also, even if we try to push the water the other way, what's going to end up happening is we're going to get just a little bit of leakage that comes through. And then if we push hard enough, we can break this, and it'll flap open the other way. And who knows if we broke it permanently or just until we push water in the opposite direction. So this is kind of our introduction. So we'd start this, and we'll see this in the lab when we do it next week. But we look at the different humps that exist on this chart here, and we realize that it's just not a perfect thing. And we're going to do our best guess model that we have for this. And here is ideal. Ideal is this is VD, I'm going to call it, the voltage of the diode, and this is ID, the current of the diode. And in an ideal case, this comes up perfectly and takes a corner and goes straight up. This is not real. You can't do that. And so what this actually kind of looks like is and this is over exaggerated a lot, is this guy comes up, there's a little bit of gap here, and then on this other side you could say that it's flat, and then we'll do railroad tracks. A long while later this thing will break down and head down the other way. And this is going to be different for every diode. Everyone has its own characteristics. If you look at more comprehensive models on this other side, they say this drops down just a little. That's the leakage current that comes through the opposite way. And we still have kind of this vertical to it, but we also have a horizontal distance here that's causing all sorts of problems. And it's not really causing problems, but it makes it to where our diode is not perfect. If we were to kind of look at this asymptotically and look at this line coming down here, by the way, these two plots completely unrelated. Let me get rid of this one so that you're not confused. If we were to look at this on a standard silicon diode, 0.7 volts. Okay, so there's lots of different kinds of diodes, and that's about how it looks. And the question is, what does that curve look like? We're going to ignore this area for right now. We're going to ignore the lower end. The upper end, we have a curve that goes upwards, and we want to know what that looks like. And some people, and so just so that we're clear, we're talking about the voltage drop across the diode and the current through the diode, just so that we're 100% clear. And what it ends up being, if you do the math, I will get to the point and then we'll go back through the math.
Do they do capital? I've got to see if they do capital D or not. I'm not sure. They aren't using a subscript at all.
So they're just saying I'm just going to say I of the diode combined is equal to, and this is what it ends up being in the very end,
I sub S, that's a constant for a diode, changes per diode.
Then E, then we have VD of the diode over VT, also a constant. And that's a constant of the material. So these two, so we've got a few things. ID we understand. VD we understand. IS is a device specific constant. Specific. It's a device specific constant. Okay? VT is, it has some variability to it. So we're also going to say it's a constant, but it can change. Okay? So, and that's actually the thing that we need to look at right now is what VT is. But that means that this is an exponential curve up, and that makes really a lot of sense. That it's not an asymptote. Obviously, exponential, it'll go forever in one direction. But there's going to be a reasonable point where your diode is going to blow up, where you're going to shove so much current through it, it's just going to melt. And it'll either fail shorted or it'll fail open. It depends on how you treat it. And let's just go through a little bit of the math. I just want to look at just this equation right here and where we got it from. First of all, people looked at the curve and they said, it looks like an exponential. And so they did that. But let's start with the VT. VT is an interesting thing. We have an equation that's very specific for it. K times T over Q. And this is where we get into semiconductor stuff. So K is Boltzmann's constant. Careful. There are two different Boltzmann's constants. Okay? And there's one that's 8.62 times 10 to the minus third or fifth electron volt per Kelvin. There's also one that is equal to, so that's the lower one. Bigger K is 1.38 times 10 to the negative 23 joules per Kelvin. Okay? Which one are we going to use? Well, it all depends, and in this particular case, I believe that we end up using this one. Okay, Q, this is one that you're going to have to memorize. This is the charge of an electron. It's the positive charge of an electron. And this was the one that you should commit to memory. 1.6 times 10 to the negative 19th coulombs. Okay? The last one is T, temperature in Kelvin. Okay? And so we're going to use this bigger one for our KT over Q. Okay? And I take that back. So we're going to be using this one for this. If you want to, we can plug it into MATLAB, and maybe I'll do that here really quickly, and we get 8.62 times 10 to the negative fifth. We're going to multiply that by the temperature. Let's just say it's room temperature, so 273 degrees. Okay, is, well, 273 plus room temperature 293 Kelvin. And then we have in the bottom of this 1.6 times 10 to the minus 19th. And when we get done with this goes, so let's just, I'm going to crank it over to the MATLAB side really quickly. You can be with me on this. I just have my little MATLAB microscript that we have on the side that's going to be with me. K is equal to 8.62 e to the minus fifth. T is equal to 293. Q is equal to 1.6 e to the minus third, e to the minus 19th. And then we go K times T divided by Q, and it gives us something awful. And so that would be the wrong K in this particular case. And so what we need to do is put in the other one, the 1.38. So K is equal to 1.38 e to the minus 23
25.3. Okay? And now we're going to go K times T over Q. This gives us 25.3 millivolts. The units on this is going to be millivolts. Okay? We call this a thermal voltage. 25.3 millivolts. This changes with temperature. We increase temperature, this value is going to go up. K is a constant, Q is a constant, but temperature is not. And there's some really nice parts about that, but that means that this constant, whatever's going on, this will change with temperature. For most of our problems, when we do this, we're just going to say 25 millivolts, and it's done. Okay? IS is the next thing that we have to worry about. So I hope that's clear. The one thing that's not clear, and it's not even clear to me, is why physicists decided that we need to have two different values for Boltzmann's constant. And I wish that they were more concise on it, but that's just the way that they are. And even in the book, I think this is really interesting. They substitute K for 8.62 times 10 to the negative fifth, and somehow they got, well, they got the first one I got, I don't even think they got that right. So I'm really confused in the book that they were able to do that, but we're going to use this one for most of our calculations. And what you're going to do is you're going to, if you don't know which one it is, put them both on your cheat sheet when you take a test. But what you're going to do is you're going to choose the one that makes more sense as far as the end result. For this one, for the KT over Q, it's the 1.38 times 10 to the negative 23rd. IS is a constant. It's dependent upon how we make the silicon, how we make the actual junction that creates this. And so that's leading into when we go back to chapter 3 on this. But IS, so I, they basically have some rules. I is going to be much bigger than IS. Okay? That's going to be one of the big rules that we have for our non-ideal diode. For this model, is that I is going to be much bigger than IS for this to be true. And specifically, I think that IS can be in the in the femto amps is where it's going to be. So it's really, really small. Okay, and so what this does for us is, if we know that, so we can just pick a value, and let's do an example that they have for us. Yeah, I'm not too worried about the other side of the stuff, but let's pick an example for this, and they just give us a test current. They say we're putting 1 milliamp through a diode, and we measure the voltage over it, and it's 0.7 volts. It's at room temperature, so we can use 25 millivolts for VT, and the question is, we want to find what IS is. Well, that's easy. This is all just plug and play. 0.7 is equal to IS E to the VD over VT. VD in this particular case is going, oops, I did that wrong. Ha! 0.001 is equal to IS E to the 0.7 over 25.3 times 10 to the negative third. And then we're going to solve for IS. Now, in a similar manner, let's rearrange this, okay, to where we can rearrange this to where it's, in terms of VD, sorry, I'm going to use the large subscript, VD is equal to, and you can do the algebra if you want on your own. It's not a super difficult equation, but this is going to end up being VT, or thermal voltage, times the natural log of I over IS. Okay? And so these are both the same thing, we just solved one for the other. And so it's good to know each way. It would have been better probably to start my problem with that one here, but what we're going to do is crank this all into MATLAB. And one thing I'm actually really liking about this setup that I have here is I can just look at mine, I can look with you, and, oops, let's get that all in there. I can look with you as I type this in, and we end up with, so ID, wow, ID is equal to 0.001, VT is equal to ants, no, 25.3, E the minus third. What else are we going to put in here? VD
is equal to 0.7. Okay, and so now we have 0.001 divided by exp of Vd over Vt, and we end up with, yeah, 1 times 10 to the negative 15th. Okay, that's what we get for this particular thing. So if we go and solve for this, that's a very, very small value. But it's just the constant we have for this. So 1 times 10 times 10e to the minus 16. I guess that would be negative 15. Anyways, it's 10, so that would be 1e to the minus 15 about is what it would be. Okay? And so that's what we would get for a value of is for this particular thing. If we change just something, if the temperature changes just slightly, there's some interesting things. So let's just change the temperature slightly to 25. Okay? We'll do, and we'll recalculate Vt. T is equal to 290. Well, I'm just going to say Vt 25e to the 25e to the minus 3. We'll do that. We'll go and run this, and it does a dramatic shift. Actually, we get a huge change in what that is, and that's because we're dealing with exponentials here. And so we have a nonlinear fit between them, and that's only part of the problem. And so that's all interesting, everything. But what we want to think about with the exponential model is fixing it. So before we move on, so that's the forward bias region. This is the best model that you can come up with for it, and we're going to go in with the problem of that. So there's still problems. Nobody wants to solve problems with this diode this way, and so let's hold off on the other stuff. Well, let's just do reverse bias really quickly. And so here, I'm just going to break it down. So we have our little bitty exponential that comes in, maybe 0.7 volts here. This comes through, we have railroad tracks, and then we have a breakdown back here. We call this breakdown, and avalanches, or there's a lot, some people call this the Zener. There's diodes that are designed to break down at a certain point, and they have a very specific purpose, and we'll talk about the very specific purpose of that. They help us do voltage regulation or clamps or other things. But those are non-destructive. Some of them we push past a certain point, and they start to, well, they smoke, okay? We can only get so much voltage through them. And so I just want to point out that much and be kind of done with this, that other side, the reverse bias region, does exist, and it's not perfect. It's going to break down. And at that breakdown, it's going to do some nasty stuff, depending on what it is. But we call that the breakdown voltage. The knee voltage, I'm looking in 4.2.3 in the 7th edition. And some of those diodes are designed to do that. Typically, they're called Zener diodes. And we'll continue on with the exponential model and how it's going to work in the next lecture.